Hello, hello, hello. This is Nicholas doing a quick sequel to my previous video on what the directional derivative actually is. That fundamentally being a linear transformation. And so we said that the directional derivative of f at a, with some velocity vector v, can be thought of instead as a derivative transformation of f at a on v. And we call this matrix representing the derivative transformation for a differentiable function f at the point A. It's called the Jacobian matrix. So that's the Jacobian. And the next question that we should probably ask is, well, what exactly is this Jacobian? Well, and also the sometimes the way you'll see it written, actually most of the time you'll see it written, is it's going to be j sub f at the point A times the velocity vector v. So in the one case here, your input is a velocity vector. In this case here, the matrix is independent of the velocity vector, but you're multiplying. You're doing matrix vector multiplication right here, whereas in this case, the vector is the input of the transformation. So now if we're to look at actually computing this Jacobian matrix, let's consider the jth column of the Jacobian matrix. That would be, if you remember from the last video, that would be the derivative transformation of f evaluated at the point A. It would be of the jth standard basis vector, which I'll write as E sub j, right? Because the jth column of a matrix represents the image of the jth standard basis vector after the linear transformation represented by that matrix has been applied. So the jth column of j f a would be then the derivative transformation corresponding to an input of the jth standard basis vector, which we could write then as a directional derivative, that being the directional derivative of the jth standard basis vector, in the directional derivative in the direction of the jth standard basis vector of the function evaluated at the point A. But realize that the directional derivative, when it is in the direction of a standard basis vector, is just a partial derivative. This is just the partial derivative of f with respect to xj. And this is such a tremendous result evaluated at the point A. This is such a tremendous result because what this tells us now is that the Jacobian matrix has columns that are just given by the partials with respect to each input variable. So in other words, j sub fa by this fact right here is literally just partial of f with respect to x1, partial of f with respect to xn. And then I haven't written in all the columns here, but that would just be the components of the whole function f. In other words, if I were to write this out all the way, it'd be the partial of f1 with respect to x1, partial of fn with respect to x1, the partial of f1 with respect to xn, the partial of fn with respect to xn. And boom, right there is the Jacobian matrix. So if you want to compute a directional derivative at any particular point with a certain velocity vector, all you have to do is find the Jacobian matrix of the function at that point in that direction and multiply, not in that direction, find the Jacobian matrix of the function at that point and then just multiply by the directional vector v, matrix vector multiplication, and you get the directional derivative at that point. Because the directional derivative is just the Jacobian times the directional vector. And with that,